All right, so things are about to get fun. Buckle up. We're going to read in a data frame of earnings from a CSV file. So make sure you've downloaded the earnings data set and put it wherever your directory is set, or set your directory to wherever you put the file and read it in. And you can look at basically what the data are, their observations, and you could say, ask how large it is, what are the dimensions of this earnings. So 1,816 by 15 variables, just under 2,000 observations, individuals. You can also look, of course, at the kind of spreadsheet by clicking under data on earnings, and you can see that we've got a couple thousand observations, and the main variables we're going to be working with are height and male, whether or not they report as male, and earnings, reported earnings. There's some other ones too if you want to play around with them, explore. So we're going to fit a very simple model to start, and it's just going to look at the relationship between two of those variables, earnings and height. Earnings, and we could actually, before we even do that, we can do model-free quick look at how earnings and height are related linearly, if at all. I can't remember if it's 1R or 2. I think I may be off. I think it's just 1R. Yeah. Earn, and actually I'll have to give the name of the data set earnings earn, and earnings height. All right, so it's not super close to 0. It's on the low moderate side. Again, there's no real clear way of saying what's a high and what's a low correlation. It really depends. If you're working with time series data, where you've got observations related to the observations at a previous time point, maybe you could regularly have correlations in that context that are like 0.89, 0.9, and so on. But with 2,000 observations, I could get a statistic estimation of, I could get a p-value that would make it clear that this is non-zero, which I certainly would not expect exactly 0 between these two, but no real meaningful magnitude. There's no way to look at this correlation and say something about the expected differences in earnings based on height. And we should say that I have no causal model here. I'm not implying if we find earnings related to height. Descriptively, I'm not implying that height somehow causes earnings, although one could come up with a theory that might explain it, or might explain other variables that height is causally connected to that in turn cause differences in earnings, but none of that is implicit in this regression. We're just comparing. And if we wanted to, we could try to predict new data. So using StanGLM, I set it to work, and as soon as that's done, we're going to take a look at the sort of basic summary. You can actually use the summary function like I do in after LM runs. You get a lot more information, but we want to keep it as simple as possible for now, since we haven't really explored the power of these methods. So it's just a lot of extra information that's not going to be super useful to us. Okay, I think what I'll probably do after this one, since these are starting to take longer, is that I'll run the quick frequentist estimation to talk about the coefficients while we're waiting for results, starting with the next model, so that I don't have to vamp unnecessarily. Well, what do you expect when we see the outcomes of our estimation, do you anticipate a positive or negative relationship? Well, I guess we already saw the correlation, so we know it's going to be positive. If you had to, there it is. If you had to guess, height is in inches and earnings is in dollars, US dollars, in terms of whether it's a meaningful difference, whether there's a substantively meaningful difference in average earnings by height. What might that look like? All right, let's take a look. All right, so intercept, not very useful to us, right? What does it say? It's literally giving you an expected value of earnings for someone who's 0 inches tall. That's not meaningful. It's way outside of actual data, and there's nothing that says that a linear model fit to data on realistic heights and realistic salaries is going to have, or earnings is going to have anything to do with unrealistic predictions. So one thing I will point out, this is the only like kind of little tidbit since it's in this output. Right, remember we've got coefficients, we've got estimates of the standard deviation, or in this case the yeah, it's actually the standard deviation of the error. But we also have this mean posterior draw, and for the time being, let's just say as a diagnostic, one thing what it's actually looking at is with this model, given the sort of variation in x values that we see, it's running a number of different plausible models relating x to y and inputting x's and simulating draws of y. So it's taking our estimated model and creating new pseudo data. And so what we want to see is we want to see a number here that's not too different from the overall mean, sample mean of earnings. And thankfully it's not. Just seeing that it's not doesn't mean that this is a good model, but if it's way off, it might be an indication that something is wrong with the model. So it's one of many diagnostics one could use to see, when we're talking about results as the best fit, if it's really, even the best fit for a model is terrible, then it's not going to be useful. Okay, so what do we have? This coefficient on height is about 1,600, right? 1,595. So what does that mean? Stick with explaining it in just a comparative way. It means that if you were to look at two people who were an inch apart in height, person who is an inch taller would be, or people with who are an inch taller are on average expected to have earnings about $1,600 more, right? And the uncertainty around that coefficient is about $127. So maybe 250 in either direction would give us a nice confidence band. And here's the, when you use that regression line to make predictions, right, there's a wide distribution around it. We'll see it with the plot of it. But, you're getting typically around 22,000 over or under the prediction given by the line. Okay, here's what we might be more used to seeing. Right, I'm really confident that height is associated in a linear fashion with weight. That's all this stars are saying. Very small p-value. It's not saying the relationship is large. It's just saying the relationship is clearly non-zero. So that's worth knowing, certainly. But otherwise, the t-value and the probability, that's a distractor from trying to interpret the relationship in meaningful ways. And you can even see, right, the r squared is 0.07. So only 7% of the variation in earnings is explained by the variation in height. That doesn't mean caused by. It just means if I take height as information, I can make slightly better guess at average earnings, right, than if I just guessed average earnings based on the overall average. If I take the information in height, I can chip away a little bit at the uncertainty. Okay, so I want to plot this, and I'm plotting. I want you to notice I'm going to draw a number of different lines to the data. Let's actually see if, yeah, okay. Let's go to here. See if this comes out. So there's the jittering. What it does is when I'm not seeing observations that are in a sort of anywhere in an interval, when they tend to fall in like, let me get the data here. When you look at the heights, if the heights are only to the nearest inch, for example, you can see in the graph they're going to fall entirely in these bands. The reason that they're actually looking like a band instead of just a line is because what I've done is added a little bit of random noise to both the x. I can't remember if it's the x and the y, but so otherwise you'd have a bunch of overlapping. You wouldn't be able to see sort of how much more data there are at certain heights than other heights. I can't remember if earnings also added a jitter. Yeah, earnings and height both got added. So there's a little bit of noise added so you can kind of see the data points separated. Otherwise, ones that are exactly the same, overlapping, someone with the same height and earnings, two people won't look any different than one. Okay, so got this axis. Now what I'm going to do is notice for I in the sample, and you can look at, actually the Sims, sounds like I'm playing a video game, but if you look, what this is, and this is the sort of Bayesian estimation of work, is it's drawing from a posterior distribution the probabilities of your intercept and height, the slope for height, different plausible pairs, and they're related to one another. The intercept you have is going to limit the possible slope that you're going to have. And so these are draws from posterior over those three parameters with the epsilon. And so now what we're going to do is randomly select from these plausible sets of parameters and draw 10 reasonable regression lines instead of just one. As a reminder, that our one regression line that we would typically get, there's nothing special about it, and it will give you a little bit of a sense of other regression lines we might have gotten, or that is to say, from the current perspective, other regression lines that are perfectly plausible given our current probability of different values for the slope and intercept. Right? Okay, so we left off here, and now we're going to draw some regression lines. So you can see a number of regression lines. They're all somewhat similar. We have 2,000 points, and so not a lot of difference. If we looked at the coefficients on those, they wouldn't be super different from one another. And you can tell by looking at the data points that it's not surprising that we don't have wildly different looking. We don't have lines that are going like negative or lines that are going much steeper positive. So I want to show you one other thing. Notice that because the data, not surprisingly, include heights that are falling in mostly a band from, I don't know, somewhere around 57 inches to 78 inches, and especially a lot of data down near 63 through 67. We don't have the intercept. We don't have what happens when height equals 0. Where is this? So let's extend the x-axis all the way to 0, so we can see where these regression lines hit the y-axis. And here it is. Right. So what's going on here? First of all, I want you to notice one thing right up front. Notice now the different regression lines, the 10 plausible regression lines. When you look at where they hit the intercept, there's a lot more uncertainty about, so there are a lot of good fits that have a range of intercepts. We don't have a lot of, where is there most similarity among these regression lines? Right where the data are. That's good, right? Because that's where the information lies. Right? We have a sense of a stronger sense of, for different heights, what earnings, what expected or mean earnings there should be in where we actually have data, right? To the extent that this is meaningful at all, and I would argue it isn't, predictions of what earnings would correspond on average to 20 inches in height doesn't make sense. We don't have data on 20-inch, a lot of people who are 20 inches in their earnings, and so we can't learn about those sort of imaginary data very well, right? So this is an extrapolation that is silly, but it reminds us that friends don't let friends extrapolate. Okay, write that down or get a tattoo and remember it.